Welcome to this podcast from the Stein Monogastric Nutrition Laboratory titled Digestible, Metabolizable, and Net Energy in Diets Containing 0, 15, or 30% wheat bran fed to growing pigs. My name is Jaworski, and this was an abstract presented at the ASAS National Meeting in July this year. This is a project we did in collaboration with my colleagues Dr. Dewen Liu and Dr. Defa Li at the China Agricultural University. The outline of the presentation today will begin with an introduction to energy systems and a brief slide on dietary fiber, and then we'll move into the materials and methods used in this experiment. Then we'll move into the results and discussion, and I'll leave you with a conclusion. The digestible and metabolizable energy systems have been extensively used in the United States for a long time now, but some researchers are now questioning the fact that these systems may overestimate the energy supplied from protein and fibrous feeds and may underestimate the energy supplied from fat and starchy feedstuffs. And this may be caused by the efficiencies of metabolizable energy utilization, which are greater for fat and starch and less for crude protein and dietary fiber. And the figure at the bottom, if you're unfamiliar with DE and ME systems, is how we calculate those. So gross energy minus fecal energy is equal to digestible energy, and metabolizable energy is equal to digestible energy minus the energy excreted in the urine and also the losses of methane energy. However, for the most part, in the calculation of metabolizable energy, methane losses are excluded from that calculation. When we begin to move into the net energy system, this system accounts for the heat increment. So you can see at the bottom figure, net energy is equal to metabolizable energy minus the heat increment. And this is the best compromise between the energy value of a feed or feedstuff and the energy requirement of the animal. Now for a quick slide on dietary fiber and its potential effects on net energy. Previous research has indicated that dietary fiber may increase gut fill, may increase GI tract size, also may increase fermentation, and this will result in energetic losses as methane, and then finally we'll get a low efficiency of metabolizable energy utilization. And due to these effects of dietary fiber, heat production should increase, thereby decreasing the net energy of the diet. However, previous research has been inconclusive with the effects of dietary fiber on heat production and net energy. The hypothesis of our experiment was that increased dietary fiber in the form of wheat bran added to a corn-soybean meal diet will increase heat production and reduce calculated values for DE, ME, and net energy when fed to growing pigs. The materials and methods that we used in this experiment were 18 growing barrows with an initial body weight of 54.4 plus or minus 4.3 kilograms, randomly allotted to a completely randomized design using 3 dietary treatments, 3 periods, 6 open circuit respiration chambers, and giving us 6 replicate pigs per treatment. The indirect calorimetry equipment, like the one shown in the picture on the right, were located at the China Agricultural University, and there were 6 of these chambers that we were able to use. And they had a volume of 7.8 cubic meters, and also oxygen, carbon dioxide, and methane were measured inside and outside the chambers at 5-minute intervals. And as you can see in the picture, the pigs were housed in a metabolism cage that was placed inside the chamber. We used 15-day periods consisting of a 7-day adaptation to experimental diets and metabolism crates. In this adaptation, pigs were fed at 2.9 times the maintenance energy requirement per day. Then the pigs moved into a 5-day balance period inside the chambers where they were fed at 2.9 times the maintenance energy requirement per day in 2 equal meals at 7 in the morning and 4 in the afternoon. At this time, the chamber doors were opened and oxygen consumption and carbon dioxide and methane production were excluded from our heat production calculations. Also at this time, when the chamber doors were opened, feces were collected and urine was collected in the morning. The chamber temperature during this 5-day balance period was maintained at 22 degrees Celsius, which was equal to the thermoneutral zone of the pigs. Next, the pigs moved into a 2-day pre-fasting period where they were fed at 1.14 times the maintenance energy requirement per day, and the chamber temperature was increased 1 degree to 23 degrees Celsius, again to compensate for the lower feed intake to keep the pigs at their thermal neutral zone. And finally, then the pigs entered a 1-day fast where we had a total urine collection, and oxygen consumption, and carbon dioxide and methane production were measured. And again, the chamber temperature was increased another degree to 24 degrees Celsius. And here in the picture on the right, you can see a pig inside the metabolism crate inside the respiration chamber during the experimental period. Here is the ingredient composition of the 3 experimental diets that were formulated. The basal diet contained corn, soybean meal, and no wheat bran, and 2 additional diets were formulated by mixing 15 or 30% wheat bran with 85 or 70% of the basal diet, respectively. The basal diet was overformulated compared with the expected requirements according to NRC 2012 to ensure that the diet containing 30% wheat bran had 0.85% standardized ileal digestible lysine and met current requirement estimates for all SID indispensable amino acids, standardized total tract digestible phosphorus, vitamins, and minerals. Here are the calculations that were used. First, we calculated heat production, abbreviated HP, according to Brouwer, 1965, that included oxygen consumption and carbon dioxide and methane production, and also urinary nitrogen losses. Retained energy, abbreviated RE, was equal to metabolizable energy intake minus heat production, and then retained energy as protein is equal to nitrogen retention multiplied by 6.25 multiplied by 5.68, which is the energy equivalent of protein. And then retained energy as lipid was equal to retained energy minus retained energy as protein. And finally, net energy is equal to retained energy plus fasting heat production divided by dry matter intake. For the statistical analysis, we used the mixed procedure of SAS, where the experimental unit was equal to the pig. The model included a fixed effect of treatment and a random effect of replicate and period, and orthogonal polynomials were developed to assess linear and quadratic effects of increasing inclusion of dietary wheat bran. Now we'll move into the results and discussion section of this experiment. First, let me take a moment to set up the graphs that I will use for the remainder of this podcast. Here, we're looking at the ingredient analysis of our 3 ingredients, where corn is in the orange bars, soybean meal is in the blue bars, and wheat bran is in the green bars. We have our response variable on the x-axis, which in this case is gross energy, and our units on the y-axis, here in kcals per kilogram, and everything is on an as-fed basis unless otherwise stated. Here we can see that wheat bran contains a slightly larger concentration of gross energy compared with corn, but soybean meal contains the largest concentration of gross energy, and this is because the soybean meal used in this experiment contains 46.9% crude protein, whereas wheat bran contains 17.3% and corn contained 8.1% crude protein. Moving on to the starch concentration, we see that corn contained the greatest amount of starch with 67.3%, and soybean meal had virtually no starch with 2.3%, and wheat bran contained 11.3% starch. And finally, looking at total dietary fiber, and this includes the soluble and insoluble dietary fiber, we see that corn contained 12.5%, soybean meal 18.6%, and wheat bran contained the greatest amount with 50.9% total dietary fiber, of which almost all the total dietary fiber was insoluble dietary fiber, because the wheat bran presented here only contained 2.9% soluble dietary fiber. Now, moving into the diet analysis, and here the basal diet is presented in the orange bars, the 15% wheat bran diet in the blue bars, and the 30% wheat bran diet in the green bars, and we see that the gross energy increases as we increase the inclusion of wheat bran in the diets. Next, as we look at the crude protein concentration of the three diets, it may look as though the crude protein concentration is increasing drastically from this graph. However, it only increases from 15.1% in the basal diet to 15.4% in the 30% wheat bran diet. And so this is a very small change in crude protein, and we believe that these diets are virtually isonitrogenous. And what we're trying to indicate here is that as we replace the corn and soybean meal with wheat bran, we were able to maintain similar crude protein concentrations in the diet. However, when we look at the starch concentration in the diets, we see that it decreases from 56.4% in the basal diet to 50.1% in the 30% wheat bran diet, indicating that as we replace corn in the basal diet with wheat bran in increasing concentrations from 15 to 30%, we begin to decrease the starch concentration. As we replace the corn with wheat bran and also replace the starch from the corn, we see here that we're replacing that starch with total dietary fiber from the wheat bran. And so total dietary fiber in the diets increased from 19% to 27.6% in the 30% wheat bran diet. So basically, what I've tried to show you is that as we increase wheat bran in the diet, we replace the starch from corn with total dietary fiber from wheat bran, and we were able to hold the crude protein concentration constant. We also saw that as we increase wheat bran in the diet, we increase the gross energy of the diet. Now, looking at the apparent total tract digestibility of gross energy, crude protein, and neutral detergent fiber, here on the x-axis, the three diets, we see that as you increase wheat bran inclusion in the diets from 15 to 30%, we get a linear decrease in the apparent total tract digestibility of gross energy, crude protein, and NDF. And we saw that gross energy decreased as we increased wheat bran inclusion, indicating that the fiber is not as digestible as starch in these diets. Also, crude protein decreased, indicating that the fiber has a way of decreasing the crude protein digestibility. And finally, we see a linear decrease in the ATTD of NDF, but not a large drop from 15 to 30% wheat bran, which may indicate that in the 15% wheat bran diet, we're already maximizing fiber fermentation or digestibility. Now, looking at methane production, we see that pigs fed the basal diet produced 4.8 liters of methane per day, which linearly decreased as pigs were fed 15 or 30% wheat bran diets, from 4.8 all the way down to 1.5 liters of methane per day. This contradicts our hypothesis because we believed that as you increase dietary fiber, we would increase fermentation, which would result in increased energetic losses as methane, but this indicates that the fiber in the basal corn-soybean meal diet may have been more fermentable and that dietary fiber in wheat bran is resistant to fermentation, which is mostly caused by the large concentration of insoluble dietary fiber in wheat bran. Now, looking at heat production in kcals per kilogram metabolic body weight, we see that pigs fed the basal diet had a 301 kcals per kilogram metabolic body weight heat production, which linearly decreased as pigs were fed 15 or 30% wheat bran diets. Again, this contradicts our hypothesis because we believed we would increase fermentation with increasing wheat bran and thus increasing heat production with increasing wheat bran. The reduced heat production may be an indication of just the reductions in apparent total tract digestibility of energy and nutrients that we're seeing with increasing wheat bran, indicating that pigs produced less heat because they did not need as much energy to metabolize more digestible nutrients. Now, looking at fasting heat production, again, in kcals per kilogram metabolic body weight, we see there is no difference in fasting heat production of pigs fed either of the three diets. And this is because there was probably not enough time for the pigs on the 15 or 30% wheat bran diets to have become adapted to these diets and therefore increasing their GI tract size, which would have increased their maintenance energy or their fasting heat production. Also, these values are in agreement with the NRC 2012 maintenance energy requirement, which is 197 kcals per kilogram metabolic body weight. Now, looking at retained energy as protein and retained energy as lipid, presented in kcals per day per kilogram metabolic body weight, we see that there is no change in retained energy as protein as pigs were fed diets with 0, 15, or 30% wheat bran, which was expected because all the diets were formulated to meet the NRC 2012 SID amino acid requirements for this weight of pig. However, as we increased wheat bran, we decreased the retained energy as lipid, and this was because there was just less energy available to the pigs fed the 15 or 30% wheat bran diets. And finally here, looking at the digestible, metabolizable, and net energy in the three diets presented in kcals per kilogram on an as-fed basis, we see that the DE, ME, and net energy all linearly decreased as we increased inclusion of wheat bran in the diets. Again, this was not due to an increase in heat production, but merely just a reduction in the apparent total tract digestibility of nutrients and energy. Looking at the utilization of energy as we increase wheat bran from 0 in the basal diet to 15 or 30% in the two wheat bran diets, we see that the DE to GE, ME to DE, NE to ME, and NE to GE ratios, or essentially the efficiency of utilizing one item for the other, decreases as we increase wheat bran in the diets. What this indicates is that as inclusion of wheat bran increases in the diets, the efficiency of utilizing energy decreases. In particular, it's showing that as we move from using starch as energy to utilizing dietary fiber as energy, we decrease the efficiency of energy utilization. Thereby, we see that the DE and ME systems overestimate the energy contribution from dietary fiber, while the net energy system is able to take that into account. In conclusion, we saw that as we increased inclusion of wheat bran, we decreased the apparent total tract digestibility of gross energy, crude protein, and neutral detergent fiber, decreased methane production, and also decreased heat production, and retained energy as lipid, and overall retained energy decreased, while we were able to keep retained energy as protein constant. And finally, we saw a decreased DE, ME, and net energy, and a decreased efficiency of energy utilization. I would like to thank my colleagues at the China Agricultural University for providing me the opportunity to conduct this research at their station in Beijing, and in particular, Dr. Defa Li for giving me this opportunity to work with his researchers. And I'd like to thank you for listening to this podcast. And if you have any further questions, you can always consult our website.